Good morning, friends. In this lecture, we are going to discuss about the uniform circular motion and the detailed study about it. The uniform circular motion, we know the circular motion, that is the body is moving along the circumference of the circle. So uniform circular motion, it is the special case of the circular motion, that is the motion of the body along the circumference of circle with constant speed. So it is called as the uniform circular motion. Now as the particle is moving along the circumference of circle, here the direction of the velocity, it is tangential to the path, but the magnitude of the velocity remains constant. As we know, the object is moving in a circular fashion, the centripetal acceleration is required, and the acceleration is with the constant magnitude and which is perpendicular to the tangential velocity. The centripetal acceleration is directed towards the center of the circular path. So it is called as the centripetal acceleration. In short, we can say in a circular motion, the acceleration along the radius towards the center of circle, it is called as the centripetal acceleration. In this diagrammatic representation, you will get clear-cut idea about the velocity, the radius or the position vector, the centripetal acceleration, and the angular velocity of the body. You can observe in this diagram, the object is moving in anti-clockwise sense of rotation. P is the position of the particle. You will find this velocity V bar, it is the tangential velocity. Okay. The R bar, it is nothing but the position or the radius vector. This A bar, it is nothing but the radial or the centripetal acceleration, which is a vector, which is shown here. It is along the radius and towards the center of circle. You will find this centripetal acceleration, it is provided by the centripetal force. So this centripetal force provides the necessary centripetal acceleration. So the centripetal force is also acting in the direction of the centripetal acceleration. Okay, so you will get here the idea about the uniform circular motion. Now we want to discuss the examples of the uniform circular motion. Around us you can observe the large number of examples like the planetary system, motion of earth around the sun, motion of moon around the earth, motion of electron around the nucleus. All these are the examples of the uniform circular motion. Now we want to find out the period of a UCM. We know the time taken by the particle performing UCM to complete one revolution. It is called as period. It is denoted with the capital letter T. Now, how we can find out the expression for the period? Now, during the time interval capital T, the distance covered by the particle is equal to the circumference of circle, and it is 2 pi r with a velocity v. By using this information, we can write time is equal to distance divided by velocity. We know the formula for time, distance divided by velocity. So here if we take time as capital T, that is a period. So in that time, the distance covered is 2 pi r and divided by velocity is v. So you will find this is an expression for the capital T, which is a symbol for the period of a UCM. So when the particle is performing the uniform circular motion, the period is calculated by using this formula. Capital T is equal to 2 pi r divided by v. Okay. Then we want to discuss about the angular speed in UCM. In the previous diagram we have seen omega, this symbol is used for to denote the angular velocity or the angular speed. Again consider the object is moving in uniform circular motion. Let us consider few symbols like small m, mass of object, v, that is a uniform speed of the object, small r, that is radius of the circle, and capital T, that is the period of revolution. Now already we have found out the expression for the period, that is a time required to complete the one revolution or to travel the distance equal to the circumference of circle. So by using this relation, capital T is equal to 2 pi r divided by v. We have seen this expression. Now we can make the equation for speed of the particle. We can change this equation by taking v on the left hand side. So v is equal to 2 pi r divided by t. You will get this is the expression for the speed, or we can say this is an expression for the velocity. Now when the circular motion is observed, then position vector of the object, it is nothing but the radius vector. So you should know here what is the radius vector and what is the position vector. The position vector and radius vector both are the same, which are drawn from center of circle to the position of the particle. So during the circular motion, as the particle move along the circumference, this radius or the position vector, it also get change. Okay. So when we consider about this radius vector, then the magnitude of this radius, it is constant, but it is a directed away from center of circle, that is away from the center of circle. That already I have told you what is a radius vector, what is a position vector. It is a vector which is along the radius and away from the center of circle. Okay, now we want to find out here the expression for omega, that is angular speed. Now we know in case of the UCM, the radius vector describe the equal angle in equal interval of time. As we draw the radius or the position vector, then you will find there will be the central angle for the given time interval, and that angle it is will be the same for the equal interval of time. So this angular speed gives the angle described by the radius vector. So this speed, angular speed, that is nothing but angle described by the radius vector. Now how we can find out the expression for this? So if we consider the one revolution, so what will be the central angle? Definitely it is a 2 pi and time required is period. So by considering one complete revolution, the angle described is 2 pi and the time required is capital T. With the help of this information, we can find out the angular speed. As we know, speed is equal to distance divided by time. The same formula you can observe here. Angular speed is equal to angular distance, that is nothing but the angle trace divided by time. So omega, it is a symbol for the angular speed. This is read as omega. So this omega is nothing but angle divided by time. In one revolution, 2 pi angle is trace and time is taken as period capital T. Now here we can take the value, or we can put the expression here, that is dividing with a small r. Now if we divide here with a small r, then you will find here this is a 2 pi r divided by t divided by r. So you will find here, that is what is taken here. So what you can observe here, what how we can find out this omega, that is angle is 2 pi, period is capital T, and it can be written as 2 pi r divided by T divided by r. And we know this is 2 pi r divided by T. This is nothing but the velocity, and r, it will remains as it is. So omega will become v divided by r. This can be written as v is equal to r omega, or you can make the equation for omega v divided by r, and this is an expression for the angular speed in UCM. So you should remember this equation, that is omega is equal to v divided by r, where v is called as the linear velocity, r is called as the radius, and omega is called as the angular speed. Okay, so the next point that we want to discuss here, that is expression for the centripetal acceleration when the particle is performing the uniform circular motion. Means we want to find out the value of or expression for the centripetal acceleration. So let us consider this a diagrammatic representation. Now we know the circular motion is a two-dimensional motion. So this is shown with the help of the center as the intersection of the XY coordinate system. So if you observe here, then position of the particle is taken at point P. Particle is performing uniform circular motion in anti-clockwise direction. Then you will find the coordinate axes are chosen as shown in figure, that is a center at lies intersection of the two coordinate axes. Now let us consider the certain symbols. If you observe capital A, that is initial position of the particle. Then P, it is the position of the particle after time t. It is called as the instantaneous position. Then theta, that is nothing but angle made by the radius vector. As we know, theta, that is the angular displacement, and this theta is given with omega into t, because omega, that is angular velocity, is equal to angular displacement divided by time. So theta is given with omega into t, where omega is called as the constant angular speed, because we know in case of uniform circular motion, the particle is moving with constant angular speed, and this r bar, it is nothing but the position vector. If you observe in the diagram, then vector op, it is denoted with r bar, which is called as the position vector. Now we are interested to find out first the position vector, because if we know the position vector, by taking the derivative we can find out the velocity, and if we know the velocity, then by taking the derivative of the velocity, we can find out the acceleration. So let us consider the position vector r bar. It is given as I cap x plus j cap y, because the coordinates at point P, it is given as x and y. Okay. Now I bar and j cap, I cap and j cap are the unit vectors along x and y axis. This already we have seen in case of scalars and vectors. Now here we can put the values of x and y. Now from the diagram you will find here x is r cos theta and y is r sin theta. You will find with the help of the trigonometric relation in the diagram. Okay, so x is replaced with r cos theta and y is replaced with r sin theta. Now this theta is replaced with omega t, that already we have seen. So I cap r cos of omega t plus j cap r sin omega t. Say this is equation number 1. So this is a very important equation for the position vector. Now we can find out the velocity by taking the rate of change of position vector. Means simply we can find out the velocity by taking the derivative of the position vector with respect to time. See, it is written as v bar is equal to d by dt of r bar. So it is called as the derivative of the position vector with respect to time. Now we can put the value of r bar by keeping d by dt. Kept d by dt as it is, and from equation 1 you can put this value of r bar, that is I cap r cos omega t plus j cap r sin omega t. Now how we can solve this derivative? While solving the derivative, here are the two terms. First we can write these two terms separately. So first term, that is I cap r cos omega t, we can take the derivative of it, and second j cap r sin omega t, we can take the separate derivative of the second term. Now we know the different rules for the solving the derivative, that for the first term you will find the constants are taken outside. So I cap and r, these are the two constants which are taken outside, and remaining factor is d by dt of cos omega t. It is written in the bracket. Similarly from the second term, j cap and r, these are taken as a constant, and derivative of the sin omega t, it is written here in the bracket. Now you should know derivative of cos, it is the minus sign, and derivative of the sine, it is the cos only. So in the first bracket you will find derivative of cos omega t, means it must have the negative sign. Constants are taken outside, I cap r, and this omega is also taken as a constant, which is the constant angular speed, and derivative of cos, it is minus sine omega t. Okay, so you'll find this is minus. So how we can find out the derivative of the second? So you will find first constant, that is a j cap r and omega, and what is the derivative of sine? Definitely cos omega t. Okay, so you will find this is nothing but the expression for the velocity. See, now here we can take common as r, common as omega. So this equation can be written as r omega as a constant, and here minus I cap sin omega t plus j cap cos omega t. Let us consider this is equation number 2, which is an expression for velocity of the particle. This is expression for velocity of the particle. Now we can find out the acceleration of the particle. It is called as the instantaneous linear acceleration. If we know the velocity, then by taking the derivative of the velocity with respect to time, we can find out the acceleration. So a bar is equal to d by dt of v bar. Now we can put the value of v from equation 2. So you will get the relation d by dt of This is the value of V bar from equation 2. Again, you will find there are two terms. So how we can find out the derivative here? R omega is taken as constant, and again we can take the derivative of these two. Okay, so we can take the derivative of these two, and the derivative of these two, it is written like this. Okay. Similarly, if we consider the next step, that is R omega, it is taken as a constant, and these are two steps, it can be written separately. That is a d by dt of minus I cap sine omega t plus d by dt of j cap cos omega t. Again, we can find out the derivative separately. See, a bar is equal to R omega. It is taken as constant. So what will be the derivative of this? Again, you will find this minus I cap. It is a constant. Omega is also taken as constant. And derivative of sine is cos. So you will find negative sign is here. So minus I cap omega cos omega t. Again, here j and omega, these two are constant, and derivative of cos omega t, it will become minus sine omega t. So here again you will find the negative sign. Okay, so here is also negative sign and here is also negative sign. So this equation can be written as negative sign is taken as common, minus r omega square, and in the bracket you will find now I cap cos omega t plus j cap sin omega t. Now we know that is the r, small r, it is a taken inside the bracket. So only minus omega square is kept outside. So r will get multiplied for this factor and for this factor also. So you will find here minus omega square I cap r cos omega t plus j cap r sin omega t. And as we know, this bracket can be replaced with the position vector that is already provided in equation number 1. Okay, so if we put this value of position vector here from equation 1, then you will find this is the final equation for the centripetal acceleration. So this is an expression for the centripetal acceleration. The negative sign indicates that the direction of the acceleration, it is opposite to the position vector. So you should remember this is the equation in the vector form. That is a cap is equal to minus omega square into r bar. In magnitude only, we can say a is equal to r omega square. Okay, so you will find this is an explanation regarding to this uniform circular motion centripetal acceleration. As we know, centripetal acceleration is nothing but a is equal to r omega square. So we can find out the necessary force which are required for to provide the centripetal acceleration, and that is the centripetal force. So the force which is necessary to keep the object in the circular path which is directed inwards towards the center of rotation. Already we have seen which is acting in the direction of centripetal acceleration. How we can find out the formula for the centripetal force? We know the magnitude of the centripetal acceleration, a is equal to r omega square, and easily we can find out the centripetal force because it provides the centripetal acceleration in the same direction. So we know the Newton's second law, force is equal to mass into acceleration. So we can put this value only in this simple formula. So force will become F is equal to ma mr omega square or mv square upon r or m omega into v. You can put all these values by taking the relation v is equal to r omega. In the vector form also we can write this equation, f bar is equal to ma bar, okay, which is equal to negative sign minus m omega square into r bar. We have seen this negative sign indicates force and position vector. They are opposite in direction. So you will find in case of the uniform circular motion, the centripetal force plays very important role, which is given by using this formula. F is equal to mr omega square, which is equal to mv square upon r, or which is equal to m omega into v. Okay.